Francisco, ready? Yeah. So welcome everybody. So today we have Özlem Yeşiltaş, and she will be talking about pseudo-Hermitian Dirac operators and on the donut. And there also you can read different variations of donut for the massless fermions. So when you're ready, just go ahead, Özlem.
Thank you very much. Thank you for all these nice contributions and organization and accepting me. So yeah, this is in fact a revisit problem of my previous study, Torus problem, the Dirac equation, and it's under magnetic fields, and its exact solutions were done, in fact. But I want to visit this problem again, but within PT-symmetric pseudo-hermiticity concepts. So I would like to start with the geometry of torus, and especially the two-dimensional zero effective mass Dirac fermions in the atomic layer of the graphene material. They are providing a feasible platform to study, and of course, on the other hand, unify fundamental concepts from the quantum fields theory, topology, and curved space-time considerations, and structure of these two-dimensional honeycomb lattice is allowing us to take into account the defects, disclinations, and gravitational effects and contributions on the surface of the graphene. And in today's works, these fields are very popular. Especially they are being studied by the both theoretical condensed matter and QFT, quantum field theoretical studies, and by these people who works in this area. In here, first we will look at the toroidal space-time. But I would like to talk about the constant Fermi velocity in here today, because position-dependent Fermi velocity case is taking much time. And I will talk about the Dirac Hamiltonian in the curved space-time and its necessary separation to the flat space-time. And I want to also talk about the scalar product, which is known as the Parker product in the curved space-time, and self-conjugacy and the uniqueness of the Hamiltonians, and the eta representation, intertwining of as an intertwining operator, considering the Dirac Hamiltonian, and pseudo-symmetric approach, which is very well known by you. And then I would like to conclude and the results. All right, so if I show you this curved graphene nanoribbons and tunneling currents, this study was, as far as I know, to my knowledge, it is first done by this Belonenko and et al. These toroidal graphene surface studies, and using the gravitational contributions. In here, the dependence of the electronic spectrum of the nanoribbon on its geometrical characteristics is revealed in this study, especially if you look at the geometry of the problem, toroidal and helical nanoribbon. And in this study, these dynamical properties and the charge carriers in two-dimensional atomic layer of graphene lattice within the, again, torus shape geometry was studied by this Shahin et al. And according to the recent experiments, the Fermi velocity is changing with position. These experiments have been able to measure the renormalization of the Fermi velocity, which is increasing near the Dirac points. Decreasing near the Dirac points. So because of the ripples in the graphene materials, this effect on the Fermi velocity can be observed. So these ripples in graphene samples and the results or influence of the lattice distortions on the electronic properties of the material are very trendy, and these are introduced in some experimental works such as Luciana and Sega, and also theoretical studies. In here, the metric tensor is given in terms of the Minkowskian metric tensor, and there is a strain tensor which is shown by U, and you can see these UIs in here and H. These are known as UI is the in and H is the out of plane displacements. So you can look at the details. You can find the related all the details in this work done by Vosmediano and et al. So the motivation behind all this recent study, I just want to show you the motivation and why I am studying this topic. It is both academic interest, and also I want to see what the difference is if I study this toroidal geometry, what happens to the energy spectrum and solutions. On the other hand, during these calculations and during the studies of mine, I have come into some very interesting results, and I want to share this with you. And I have no idea if they are important or not. I just want to start with the, of course, the Dirac equation in curved space-time. It is including many geometrical objects. Of course, we can start with the gamma, Dirac gamma matrices in the curved space-time. So we shall transform these matrices into the flat space-time, and using some other geometrical objects such as tetrad fields and connections, spin-affine connections, and Christoffel symbols. And you can see the spin commutator in here. Especially, we can also use the facts that the covariance derivative of the tetrads is vanishing. And of course, I just want to show you the inner and outer radius of the torus, and this is the parametric representation for this torus. In the previous study, the people were using x1 and x2 for the coordinates. So this is corresponding to inner, C is corresponding to outer radius. And I would like to give you the metric tensor and the Feldbein one forms, and the corresponding vectors can be calculated with respect to this DS2. And I would like to use instead of x0, I want to use tau, especially this tau can be expressed in terms of Fermi velocity, and x1 and x2 can be used as v and u. So according to this, and according to the local and global indices, these gamma matrices are given in the flat spacetime. These are corresponding to the gamma matrices in the curved spacetime. So our tetrad fields are the geometrical objects that are linking these two matrices. And we can also express the metric tensor in terms of our tetrad field, tetrad 1-1 forms. So they are, as far as I know, a set of 4 linearly independent vectors. And I also would like to show you the angle for considering this torus from these u and v. These are changing from O to 2 pi. Yes, I just continue. And our calculations, according to the calculations, we can obtain the Christoffel-Semmelweis and the spin-off-in connection. And I am using the standard representation for the gamma matrices. And one can also look at in the 2+1 dimensional gravity. One can look at this in this space-time. One can look at the chirality operator and hermiticity condition we can use. On the other hand, you can look at the field strength can be given in terms of this commutator of this covariance derivative operators. These are expressed in terms of the Riemannian curvature tensors. So one can also calculate these elements for torus. And one can reduce this problem in Minkowskian flat spacetimes, curved space, from curved spacetime to the flat spacetime. And also we can reduce the problem. And of course, we can separate the Dirac equation. In this separation, I am still using the x1 and x2. This R script is corresponding to this cosine x. It can be given in terms of cosine x function, c plus a cosine x. And I want to use this del x0 for the time component, 1 over Fermi velocity del t. All right, so I would like to continue with the hermiticity and non-Hermitian operators and related aspects in the curved spacetime. Using this a couple of differential equations, one can generate a Schrödinger-like second-order differential equation, and one can look at its exact solutions. In my previous study, I look at the exact solutions, in fact, but this time I would like to first remind you the scalar product in the curved spacetime. In fact, it was done by Parker in 1980 before, and I would like to give you a list of important and popular works by Arminjon and Gorbatenko et al., which were published 10 years ago. But of course, the gravitational fields described by the metric g mu nu xt or rt, it is always necessary to find the system of tetrad vectors satisfying the Schwinger gauge. So you can find the Schwinger gauge and the self-conjugacy and uniqueness of the Hamiltonians in this study. So I'm not mentioning these aspects in here. And of course, it is very interesting to see that a scalar product done in the curved space-time using the Parker's weight operator, because I was not interested in the curved space-time calculations, but when I look at the Parker's paper, it was fascinating for me. And when I also look at the Gorbatenko and related studies, these studies may be trendy. Of course, the pseudo-Hermitian quantum mechanics and its methods for the arbitrary time-dependent gravitational fields, one can construct an algorithm to transform the Dirac system in the curved space-time with using an arbitrary choice of the tetrads, and you can transform them into eta representation. And we will use the Parker's weight operator in the scalar product. And the thing is, of course, in all cases, the physical properties remaining identical. And in fact, Parker's study was constructed in Fermi's paper. There is, if there is any curve in Riemannian manifold, it is possible to introduce coordinates near this curve in such a way that these Christoffel symbols vanish along the curve, leaving the metric there rectangular. Following his work, Parker developed the scalar product, and using the geometry of the curved space-time, using the metric, and you can look at the integrants. You can see this curved space-time gamma matrices in here, and you can see the negative. If you take the sign negative, positive, positive, and positive in the curved space-time, it can be changing as considering the time-like and space-like forms. And if you use this determinant of the metric tensor inside of this integral, you can define the scalar products, and it should be conserved. And according to the Parker products, anyway, which is given in here, which is given below, we can see that this time derivative of this determinant of the metric tensor and the square and gamma 0x psi, and you can see that transformation, and there is volume elements. And in this study, I tried to show the pseudo-hermiticity for a 2+1 dimensional curved space-time, but I was using the Duster space-time, which is different, and you could see the time dependency in some ingredients in this paper. But it was published in 2015, then I forgot this topic and I devoted to some different works. Now these are the fundamental aspects which are very well known by you. Fundamental aspects of the pseudo-Hermitian quantum mechanics. You can see these properties, especially the eta representation and the pseudo-Hermitian operator, which is L, is shown, and using the similarity transformation, you can get its Hermitian equivalent of this operator using the eta hermiticity and eta representation. And unique and self-conjugate Dirac Hamiltonians in gravitational fields using the Schwinger gauge leads this system of tetrad vectors. As I told you, they remain the same in the eta representation. So in the paper, in the work done by Gorbatenko and Neznamov, it was shown that this eta is corresponding to this determinant of the metric tensor. It is related to the 1 for divided by 4, and there is also the contravariant G00 elements. So one can use this description of eta in pseudo-Hermitian quantum mechanical theory. So this is the inner product which is defined in here. So I also want to show you the N2 supersymmetric algebra. Of course, we have a self-adjoint operator, and these Q's are corresponding to supercharge operators. And in case of N2 supersymmetric algebra, we have two supercharge operators, and you can consider their these combinations, and they are satisfying the algebra. The n-type commutation is giving us the Hamiltonian operator, and the squares of these operators are equal to 0. So the Hamiltonian operator is also making this this commutation is commuting with the Witten parity operator. It is 0. So this Witten parity operator is the n-type commutation of the charge supercharge operators is also equal to 0. So I want to pass these details because they are very well known.
Yes. Can I interrupt you? Philip has a question. Philip, you want to ask a question?
I can open the window. Yes.
Yes. Hi. Good morning. Can you? It's very nice to see the emergence of the pseudo-Hermitian Hamiltonian, but what happens to the 2+1 Dirac equation in flat space? Do you have that same issue there, and
yes,
or
yes.
just because of the torus?
Yes. Yes. I am coming close to here.
Thank you.
I'm sorry if I making you very bored about this stuff because I'm sure that it is very well known by you. So I just want to continue. This is the Parker's studies, including the details of the inner products, and I'm passing it. Yes. Now, this is the eta hermiticity representation for the flat space case, and this Hamiltonian is generally is given for the flat space-time. Especially the relationship in here is also given for the flat space-time. So this is the eta operator. So when it comes to the torus system, using the standard representation, I obtained this operator. And I want to switch from the coordinates x in order to lack of simplicity. So I can, of course, use the eta hermiticity to construct this torus Hamiltonian. So when I look at the system, if I use this convenient eta operator, I can obtain the Hermitian counterpart of this torus Hamiltonian. If I use this eta 2, so I will also show what eta 2 is, which is given in here, because if you remember, yeah, in here you can see this relation. So I'm changing the different notation. I'm using the notation eta 2, for example, instead of this eta tilde. If I apply this formulation, I can get the Hermitian counterpart of the torus Hamiltonian. So in the next, I wonder what is the partner of the torus, the Hamiltonian of the torus. And the next question, if I find the metric operator, so can I find another metric operator which is linking this torus Hamiltonian to the partner Hamiltonian? And also the other question is, how about using the partner metric tensor, which is related to the partner Hamiltonian of the toroidal Hamiltonian? So in order to continue with the intertwining operator, using eta operator as intertwining operator in the pseudo-supersymmetric, I just want to remember the two Hamiltonians which are given as a product of these two operators A and B. So there is such a relationship between them. So the HSN's this Hamiltonian is partner of that Hamiltonian. So in here, first of all, if you give these operators as first order differential operators, and the B is the adjoint of this operator, and there is such a relationship which is intertwining relation. There is eta 1 hermiticity in here. So these are the B orthonormal system and their aspects. So there is eta 2 pseudo-hermiticity in here. So I'm using the toroidal Hamiltonian and its Hermitian counterpart using this eta 2 pseudo-Hermitian theory. I did something wrong, I suppose, yes. And I can see that there is relationships between the eta 1, eta 2, and the products of these two eta operators are giving us the eta operator. This eta operator is linking the partner Hamiltonian to the partner Hamiltonian's Hermitian equivalent. So I'm using these aspects in this study. So if the torus Hamiltonian is eta 2 pseudo-Hermitian, I can find its partner. So this partner, I'm using this partner Hamiltonian using the eta 1 hermiticity. So I can calculate this partner Hamiltonian, including this eta 1x operator. This can wait for a while. This is equation 1. And on the other hand, I can use the Hermitian equivalent Hamiltonian of the torus torus Hamiltonian. So I can use this formula in order to get the partner Hamiltonian again. And I can compare these two Hamiltonians. So from here, I can express the eta operator in terms of this Rx, R script X was known in terms of the torus parameters, and the eta 1x. So I know the eta 1x, so I can, of course, give the eta 1 in terms of the metric tensor determinants and its time components. Now, according to these results, I want to ask a question. If I obtain the flat space-time, the Hamiltonian, the torus Hamiltonian in the flat space-time, and if I obtain this Hamiltonian by using the geometry, there is also a partner of this Hamiltonian. So what is metric tensor? What kind of thing it is? So if I want to get this from the curved space-time HP Hamiltonian. So I just look at these results that I obtained, and I give an ansatz, okay? So according to this ansatz, there is a term eta x is appearing in here. So I think there is a term A is forgotten in here, inside of this square root. So in here, I just want to add another coordinate in the matrix. So this means that it's a kind of expansion. So I'm adding this eta x square by hand. So the metric tensor for the torus Hamiltonian, and this is the partner of the torus Hamiltonian. So this can be the corresponding metric tensor for this partner Hamiltonian. So these are the results of the this recent study of me. In the second part of this study, there is, of course, the exact solutions of the system using the analysis and special functions. And on the other hand, I am, of course, studying in the topic of the position-dependent Fermi velocity. So thank you for listening me. So I just want to share this nice picture and words by Carl Sagan.
Thank you very much.
Thank you very much. I thank you. So I just try to open the windows.
Philip has a question.
Okay, I have quite a few, but let me go back to the one I asked initially. What can you just tell us about pure flat space 2+1 Dirac equation? Is there anything there that would lead you to non-hermiticity or to pseudo-hermiticity?
Oh, yes, I see. In fact, there is, using the standard approach, using these matrices, I am obtaining and I am transforming. In fact, I didn't include the operator. Let me show the operator. I want to, yes. This is the system. When I look at the system, and if I take this Fermi velocity as changing with position, then the system becomes non-Hermitian. It becomes some general equation with the coefficients. and according to the boundary conditions, so the problem becomes non-Hermitian. I just want to introduce this constant Fermi velocity in here in order to make the problem as easier. But in the second part of my study, there is a non-Hermitian operator. And when it comes to the torus flat space-time Hamiltonian, as you said, in here, for example, in my system, there is no time dependency. So I can, maybe I can ask a question. How about the radius, inner and outer radius, this radius changing with time? Was it a physical problem which makes sense? I don't know. I don't have any idea. But the De Sitter problem, I was using the whole representation, which is given in here. But when I look at my system, which is given here, if I take the Fermi velocity at the beginning as position dependence, I couldn't show this operator in here. I'm sorry about that. Then the problem becomes non-Hermitian. And of course, the many elements are changing in this Hamiltonian operator because of the position dependency. I just want to introduce the some aspects of the theory. And because my study is not finished yet, and after maybe in 1 or 2 months, I want to submit my study to a journal. But of course, it may not look like pseudo-Hermitian or non-Hermitian. But the thing is, if I take this term as position dependent, this Hamiltonian becomes non-Hermitian operator.
Yeah, no, that's not my question. My question is, if I take the regular Dirac equation,
yes.
which in your language would mean with VF equals 1, and I just write it down, and I've never heard anything about pseudo-hermiticity, and I don't have a torus, I'm just in flat 2+1 space, would I discover that there's something wrong with hermiticity? And once you make VF a function of X, then I agree with you, but that's not what we would call the 2+1 dimensional Dirac equation.
Yes, yes. In the 2+1, yeah, because the all phenomena were generally done for the 3-dimensional or 3+1 Dirac equation.
Yes.
And when it comes to 2+1, of course, you're right. If I turn back to the beginning of this problem, yes, in here, for example, it is, of course, it is not quite clear in here. Yes.
Okay, can you hold that picture? I have another, I'll get to my second question. If you could show us the picture of the torus.
Oh yes, the torus.
Thank you. Now,
this is of course not my figure. It's from
No, but my question will become clear if we have this picture in front of us.
Yes.
If you could go back to the picture of the torus, please. Oh, all right. Well, this one is better. Yes. Now, if I just take a rectangular plane.
Oh, sorry.
A plane, and I identify the 2 opposite sides, then I get a cylinder. Yes. If I then identify the end caps, I get a torus.
Yeah.
But the geometry is locally flat because I started with a rectangular plane. So how do I get an induced metric on the torus, which is not trivial, Or is it simply because the torus is a finite size?
Yes, yes. That is the other detail.
Okay,
So,
if you think it's because the torus is a finite size, then I believe that
yes.
if you were to let the radius of the torus go to infinity,
All right.
you would come back to a regular flat space, regular 2+1 dimensional Dirac equation, which is Hermitian in the usual sense.
Yes. Yes.
That's what I would think would happen.
Yes. I think the problem of the space-dependent Fermi velocity, if I consider this and if I use the transformation to the Schrödinger-like differential equation system, then this system becomes non-Hermitian. But of course, in the point of view, this is, of course, the radius in this limit of infinity, it is Hermitian, the operator.
Maybe you could show us the Riemann tensor for this metric that you have written.
Oh yes.
And
In fact, it is. Oh,
I think you did have it at some point.
Yes, in here. Yeah.
Okay, so if I let C go to infinity.
Yes.
But no, it doesn't. No, it doesn't go to. It doesn't become. It doesn't vanish if C goes to infinity, because this R1221 won't vanish. So there's no limit on your parameters in which this becomes flat.
Oh yes. Thank you. Thank you. So
then there's something I don't understand.
Okay. Okay. So I will think about it very in detail. It's an important detail. Thank you.
Okay.
And so I was just considering that field strength and the this commutator, including this covariant derivatives. I was looking at the problem if there is such a link between this strain tensor and Riemannian curvature tensor for this toroidal geometry. Maybe this problem may be expanded into 3+1. And I'm not sure if the results, when I look at this mathematical, the relationships and mathematical equations and their results, for a non-Hermitian operator, does it make sense or not? If someone can talk about if there is a partner Hamiltonian, and are there any partner metric tensor for a given Hamiltonian in the curved space-time and related things? Can we use this term? I just wonder.
Okay.
Okay. All right. So I will consider your points, and I would like to thank you because I haven't sent this article to any journal yet, and this is very important for me.
Okay.
I also have a question. Can I ask one question? In these solutions you found for the metric, can you see somehow where it breaks down? Usually we have a region which is PT symmetric. Yeah, you don't really speak about PT symmetry.
Yes.
And then we have a region which is usually referred to as spontaneously broken regime. And the point of intersection is called the exceptional point, which you usually see in your metric that breaks down. Do you have any special points there where it becomes undefined, and what would that possibly mean in this context?
Oh yes, so in fact, I really don't know. I really don't know. Okay.
Okay.
But there is something maybe I couldn't see now, but I have to dig this topic much more, I guess.
I don't want to disagree with Andreas, but you have broken and unbroken PT in flat space time, and nothing funny happens to the metric. I think the quantity that gets problematic is the similarity transformation that transforms the Hamiltonian to a diagonal form.
Yes.
Yeah, but the similarity transformation is related to the metric. If you take the similarity transformation,
oh, you're talking about
square it, then you have a metric. Yeah.
Are you talking about the Hilbert space metric or the space time?
Yes, of course, of course.
Yeah.
I'm sorry. Okay.
But I'm drawing an analogy here. She maps Hermitian Hamiltonians to non-Hermitian Hamiltonians. So in that sense, it's completely equivalent.
Okay, so there's a problem with the Hilbert space metric, but not the space-time metric.
That's what but the eta I'm talking about.
Yeah, eta.
Okay,
And that eta is related to the Hilbert space metric. So the eta I would expect to break down at some point. And that would, in analogy, be the exceptional point, of course. Yeah.
Yes.
That's fine. That would
Maybe I should have shown the this at the beginning. Maybe I should talk more about these representations and introduced by Parker's paper, which is a recent paper of him. And in his paper, he is constructing this inner product in Hilbert space and using the aspects of the metric tensor and its geometrical aspects, the time elements and the determinants of the metric tensor, and related the completeness and the inner products relationships. In the Neznamov paper, so I think it was given, yeah, in here, this eta was given in terms of the metric tensor. And in the contents, Schwinger gauge is being used in here in order to express this eta. So according to that representation of the eta, I was thinking if there is a link between the eta and the construction of this hierarchy in the Hamiltonians. For example, if we consider the supersymmetric quantum mechanics very conventional, there is hierarchy between the Hamiltonians. Can we construct the same hierarchy in the in this representation, or one can maybe can define this theory in eta representation? For example, the supersymmetric quantum mechanics, I think, as far as I know, it is not done in this representation of the eta, I guess.
Yeah, thank you.
Thank you. I thank you for your joining and for your contributions, which are very valuable for me.
Anyone else has a question? Well, if not, let's thank Özlem again. Thank you very much.
Very much. Thank you so much. Thank you for everything, listening me and joining us. Thank you. And I wish you healthy days and take care of you. Please stay safe.
You too. Thank you.
Thank you.